Okay, welcome back. We're going to pick up where we left off, and we're going to discuss the organization of the periodic table and how we find different things on the periodic table. And like I said, these first few lessons, there's a lot of vocabulary. And I understand, there's a lot of vocabulary. So if you feel a little overwhelmed right now, don't worry about that. What you need to do is use those study slides in the workbook I have posted, and work with the words, and they'll come to you. Okay. Periodic table in general is a tool that is used to organize information about the elements. So that should be a big surprise. There's more than 118 known elements. Now, the only thing different between one element and the next element, as I said earlier, is the number of protons. So we know about elements that have up to 118 protons. Okay. Any atomic number above 93 is made in the laboratory. So what they do is they take like a uranium and they shoot protons into it until they stick. And then it turns into the next element next to it on the periodic table. And what happens, though, is these elements are not stable on Earth. Because remember, you have all those positive charges in the nucleus. So when you get past, and like charges repel. So, and that's why uranium is unstable, and you can split it in a nuclear reactor like a power plant like Anna. Because you have 93 positives repelling each other. So they want to push the nucleus apart. Because like charges repel, so you have 93 charges repelling and pushing the nucleus apart. When you get past that point, it won't stay. So they create these things in the laboratory, and they, just really to find out what they are, and they disintegrate almost immediately. We also know from the very first unit that elements can combine to form compounds. So that was, back to Dalton. Okay. Now, Dmitri Mendeleev was the first one who organized the periodic table, and what he did is he was a card player, so he would write down the properties of the elements on these cards, and he started organizing them by their properties and how they reacted. So he found out that certain elements were similar in what they reacted with to other elements. So, for example, he found out that sodium is very similar in the way it reacts to potassium. So he put them in the same column and said, well, they must be like in a family. They have similar characteristics, okay? Because they both reacted with chlorine to make salt. So, when he was doing this, he had no way of knowing what the atomic number was. But he could find the mass of things, so he organized his elements by atomic mass. This is not the way we do it today. Today we organize them by atomic number. Now, if you look at the periodic table, organizing by atomic mass and atomic number, you end up with almost the same order. There's only a few exceptions. The vertical columns going up and down, how Mendeleev was organizing these things by their characteristics, are called families or groups. And the reason why they're called a family or a group is because they have similar characteristics. So, people who belong to a group, like if you belong to FFA, you have some similar characteristics. They're all interested in the same thing. But people in a family have similar, they share some genes, so they have similar characteristics. So, that's where the name came from, because of their characteristics. Elements in the same group, as I explained earlier, have the same number of electrons in their outer energy level. Each energy level holds a maximum number of electrons, and when it's full, the electrons go into the next energy level. The electrons on the outermost energy level are called the valence electrons. I'm going to take a look at the periodic table and apply what we just learned. Okay. There are 8 main families or groups that we're going to be dealing with in the 8th grade. There's family 1, so every element in family 1 has similar properties and similar characteristics. Lithium, sodium, potassium, rubidium, cesium, and francium all have similar characteristics, and they would all have one valence electron. Elements in family 2, like we looked at that model of beryllium, it had 2 valence electrons. Okay, so magnesium, calcium, strontium, barium, and radium all have 2 valence electrons. So that's one of the properties they have in common. These elements in the middle are called transition. They transition from 2 valence electrons to 3 valence electrons. This is something you're going to focus on, these elements, if you take chemistry in high school. So for middle school, we're just concerned with how the valence electrons change. So we skip over these families here in the middle where they're called transition elements. So they're transitioning from being like 2s to being like 3s. The next main family over is family 4, where carbon is silicon, germanium, tin, lead. Okay, these all have 4 valence electrons. Family 5, nitrogen, phosphorus, arsenic, antimony, and bismuth all have 5 valence electrons, so they're in family 5. Family 6 is oxygen family here, oxygen, sulfur, selenium, tellurium, and polonium all have 6 valence electrons. Family 7, okay, fluorine, all these are the enes. Okay, everything in here ends with INE, fluorine, chlorine, bromine, iodine, acetine. Okay, they all have 7 valence electrons. And then there's finally family 8, which these are actually called noble gases: helium, neon, argon, krypton, xenon, and radon. And they all have 8 valence electrons, except for this first one, helium, which has 2. Okay, so just to review what we just saw on the slide of the periodic table, okay, families or groups are in the vertical columns. The elements in each group have the same number of electrons in their outer energy level, and those outer energy levels are called valence electrons. Okay, so we just pointed out on the periodic table, the family or group tells you the number of valence electrons. So as I just explained on that diagram of the periodic table, family 1 has 1 valence electron. Family 2 has 2 valence electrons. I explained we skip family 3 to 12 in the middle. They're called transition elements. Okay? And for 13 to 18, you just drop the 1 in front. So this is family 3, family 4, family 5, family 6, family 7, and family 8. So family 3 has 3 valence electrons. Family 4 or 14 has 4. Family 15 or 5 has 5. Family 16 or 6 has 6. Family 7 has 7. Family 8 or 18 has 8. Each row, the periods going across, ends when the outer energy level is full. It ends at group 18. And it's full when it has 8 valence electrons. So 8 is the magic number to get a full valence level. All except for the first row where helium is, it's filled when there is 2. Okay, except for the first row, which only means 2 where helium is. Now remember when we looked at that Bohr model of beryllium, and I said notice that there's 2 valence electrons on the first energy level and it's full? That's the that's this rule right here. Now, because these valence electrons are so important, like really they're the only ones that matter in chemistry, scientists chemists use something called a Lewis dot diagram. It uses the element symbols and dots to represent the electrons. So lithium is in family 1, and we see up here it would have 1 valence electron, so there would be 1 dot in its dot diagram. And this dot represents this 1 valence electron. So it tells us the characteristics of this element. Beryllium has 2 dots, and it's in family 2, so the 2 dots represent those 2 outermost electrons, which are called valence electrons. And guess what? Family 3 has 3 valence electrons. So there's 3 dots in its dot diagram. In family 4, sometimes it's labeled 14, okay, has 4 valence electrons. Okay, so it has 4 dots in its dot diagram. Family 5 has 5 dots in its dot diagram to represent these 5 valence electrons. And every element in each of these families has the same number of dots, because what's similar about a family are the valence electrons. Oxygen is in family 6, so it would have 6 dot diagrams around its element symbol to represent that it's in family 6 and it has 6 valence electrons. Fluorine in family 7 would have 7 dots. And we're going to go in pairs around the element. So there's one, and then there's a pair, and then we go here, and there's 2 pairs, and we go here. So we're going in pairs around the element. And finally, family 8 has this full outer energy level of 8. And so neon in family 8, one of the noble gases, would have 8 dots in this dot diagram. Let's see how all this relates to the periodic table. Okay. As we said, there are 8 main families that we're going to deal with. Those are the ones that we just labeled in the notes. Family 1, where hydrogen, lithium, sodium, potassium is, beryllium, magnesium is, all of this in family 2. We're skipping over these in middle school. These are called transition elements. Like I explained before, they transition from being like 2s to being like 3s. Family 4, family 5, family 6, family 7, and family 8. The only element in family 8 that doesn't have 2 valence electrons is helium, which is on this first row where there's only 1, 2 elements. That's why that first energy level is filled when it has 2. So the dot diagram for every element in family 1 would have 1 dot. So on the quiz, if I said, what is the dot diagram for francium, okay, it would have 1 dot. Potassium would have 1 dot. Lithium would have 1 dot. Rubidium would have 1 dot. Every element in family 2 has 2 valence electrons, so they would all get 2 dots if we made a dot diagram. Family 3 has 3 valence electrons, so they would have 3 dots, and every element here, its symbol, like this galenium, would have 3 dots in its dot diagram. Indium, all of them would be the same with 3 dots around the element symbol. Carbon, okay, in the little diagram on the other page, we have the carbon with its 4 dots around its dot diagram. Silicon would look the same way. Germanium, all of these elements in this family would have 4 dots in their dot diagram. Family 5, where we said there's 5 valence electrons, every element in family 5 would have 5 dots in its dot diagram. Family 6, like oxygen, sulfur, selenium, they would all have 5 dots in their dot diagram. Family 7 would all have 7 dots in their dot diagram. And finally, family 8, with the exception of helium, neon, argon, krypton, xenon, and radon all have 8 dots in their dot diagram. Helium would have 2. Elements in the same group also have similar properties. Okay, and they have similar properties because of those valence electrons. So the valence electrons, remember I said those are the important ones, the only ones that we're really going to worry about, and they're the ones that give elements their properties, and that's why Mendeleev was organizing them by their properties and putting them into the columns, because when chemical reactions happen, he noticed that those elements would react with the same things and kind of act the same way. So he said, well, there must be something, similar about these, and I'll call them a family. The horizontal rows going across are called periods. In each period, as we go like from hydrogen to helium, the atomic number goes up by 1. The period tells you the number of energy levels. So remember I said in that first model that we did of beryllium, it had 2 energy levels, so we would expect it to be on period 2. So the period tells us the number of energy levels for that element. So I want to look at the periodic table again and see how what we just learned relates to that. So period 1, hydrogen and helium would both have one energy level. And that's why that first energy level is filled when it has 2 electrons. Because see, helium has 2 positive protons. The atom is neutral, so 2 negative electrons would cancel it, and it has 1 energy level, so it's done. That's all the electrons that can fit on period 1. Period 2 has every element on here, like the model we looked at of beryllium that had 2 energy levels. Lithium has 2 energy levels. Boron, carbon, nitrogen, oxygen, fluorine, neon, they all have 2 energy levels, each of those elements. Okay, so they're all on period 2. Period 3 with sodium, magnesium, aluminum, phosphorus, sulfur, chlorine, and argon all have 3 elements. So we have 2, 8, 8, and then we have period 4. Okay, all of these have 4 energy levels in their models. Period 5, every element on here has 5 energy levels. Period 6, where cesium, barium, all have 6 energy levels. Now you see this star here, and it says 57 to 70, and then down here there's a star, and we have 57 to 70. What that means is these elements could actually be stuck right in here. The reason why they're cut out and put down here is so that this thing would fit on a page better. So this is also part of period 6. So it's like it goes 56, 55, 56, and then stuck in here where they got this little box should be 57 to 70, and then it picks back up 71 here. And then you see the same kind of thing here. It has 2 stars here, it has 2 stars here, so it goes 87, 88, 89 to 102, and then here is 103. So period 6 goes kind of like whoop, and then there's a little detour down here from 70, and then back up here, and then there's period 7, and then it's also here. So what we know so far, as far as we've gotten on Earth, is that there's a maximum number of 7 energy levels in any of the models for these atoms. We're going to leave off here, and you're going to answer these questions alone, and we'll pick up here next time.